I want to get into some applications of parametric equations, specifically with what we call projectile motion. I want to define that for you, and then we'll do an example. So projectile motion, let's just say we have this, say someone's hitting a golf ball, throwing a ball up into the air, hitting a baseball, kicking a football, anything like that, kicking a soccer ball, anything like that, in which here we have the horizontal, and then you've got this path. Initially, the path here, let's say we call it theta. Let's say that whatever you hit up or kick up into the air, you're gonna kick it up at an angle or hit it up at an angle, and it's also going to have an initial velocity, and we're going to call that v of 0. Okay, it might even be at a height of, let's say, here's the ground. Okay, let's say that's the ground, and then let's say the height right here, the height off the ground. Let's say you're throwing like a pitcher throwing or I guess that wouldn't throw it way up like that, but let's say a baseball player is throwing a ball from a height of 6 feet and up into the air, and then somebody catches it later on. But anyway, there's always an angle theta, and there's always an initial velocity. And we can use parametric equations to describe this, and this is pretty cool. We're going to do this in class on the calculator. But the x-coordinate of any point along the way, or like the x-coordinate of where that particular moving object is along the way, is defined to be the initial velocity multiplied by the cosine of theta, the initial angle, multiplied by t, and then the y is equal to negative 1/2 g times t squared, g for gravity, plus, and then v of 0, v sub 0, multiplied by the sine of theta, and multiply that by t, and then we're going to add the h for the height of the particular object. Okay, so those are the two parametric equations, and I could be talked into making you guys memorize those, or I could be talked into just giving you guys those and then having you fill those in. So leaving those up on the whiteboard or giving you. So I could be talked into either one. If you guys want a challenge, you'd like to memorize those equations. Normally they're given to you anyway, and in this particular book they're not given to you. You have to actually remember them. So anyway, we could talk about that in class. Let's go ahead and do an example. Applications of parametric equations, as I just mentioned. Suppose that Jared, and specifically Jared Pierce, hit a golf ball with an initial velocity of 150 feet per second at an angle of 30 degrees to the horizontal. Okay, how long was the ball in the air? And you can see the other questions here. So let's first of all, let's determine what the parametric equations are for this particular example, and let's do those in green. So the x would be, and if you remember back to the last slide, the x is the initial velocity multiplied by cosine. So x and cosine are again related. Okay, so we have the initial velocity, which was 150 feet per second. Okay, so 150 multiplied by the cosine, and the initial angle was 30 degrees. Okay, 30 degrees, and we're going to multiply that by t. Okay, now the y. The y is the negative 1/2 times the g. Now what's the g? And let's do this we have to look here. It's feet per second, so we're in standard measurement, and gravity is negative 32 feet per second. And so we're going to use a 32 right here. Okay, and then that gets multiplied by t squared. And then we're going to add to that the initial velocity, 150, multiplied by the sine of 30 degrees multiplied by t, and then plus the height, and the height here is 0. Okay, didn't need that green line. And so what are we trying to figure out? How long was the golf ball in the air? To determine how long it was in the air, we just have to figure out where the y is equal to 0. Let's draw a picture of this and let's see what's going on. So the ball is here, and the ball is being hit up into the air. and it's going to come down over here. Okay, well, anywhere along the way, let's make sure we understand what's going on here. Anywhere along the way, there's an x and a y coordinate. Anywhere along the way, x and a y coordinate. I should really, let's say an x1, y1, and an x2, y2, just to make it, give them distinct coordinates. And then right over here is where t is equal to 0. We could figure out where that is. We'll just put that right at the origin. T is equal to 0. And then over here, we don't know when the ball hits the ground, but we do know that the ball hits the ground at some point, because you know how that goes. Throw something up in the air, or hit something in the air, and it's going to hit the ground. So how long was the ball in the air? Well, to determine the length of time the ball is in the air, we solve the equation y equals 0. Okay, so why do we do that? Y equals 0. Well, if we solve y equals 0, we figure out what the t value is when, oops, these conflicting things here. We know that right here, the y is equal to 0 at both of these locations. In other words, the y coordinate of these 2 points is the same, and the y coordinate of those 2 points is 0. We know the y coordinate of the point where the ball starts at is 0, and then if we figure out, well, what's the t when the y is 0 over here, well, then we know how long the ball is in the air. Okay, and so I guess I could pick this up on the next slide. Let's see here. How can we best do this? So the best way to do this is to take this equation here, or take this function right here, and type that into the calculator. And unfortunately on the iPad here I don't have access to the calculator to show you that. But if this is going to be your y, let this be your y1. Okay. If this is your y1 and you set y1 equal to 0 on the calculator, you're going to get a value of t is approximately equal to 4.688. 4.688. Okay, and I want you to store that value, store that. Store, and then I normally store it in A, okay? And so the y coordinate is 0 when t is equal to this value. That means that the ball was in the air for 4.688 seconds. Okay, and S would be fine there. And then, we're already 8 minutes here. When was the ball at its maximum height? Well, notice that this particular function here is a quadratic function. And the height y of the ball is a quadratic function of t, so the max height of the ball can be determined by finding the vertex here. Let me do that in a different color. So right up here somewhere in between when the ball was hit and when the ball landed, somewhere in there you can find the maximum height. Or when was the ball at max height? Well, the ball was at its max height halfway between when it was struck and then when it hit the ground. So you could take half of that value, and half of that would be at 2.344 seconds. Okay, and so half its max height was, let's get this up here, 2.344 seconds is when it was. And what is the maximum height? Well, the maximum height then would be, well, what is the y coordinate at 2.344? And so I'm getting really messy here. So to find the answer for part C, we want to take the y of the 2.344. In fact, a better approximation would be y at that 1/2 of that value that we plugged in. Okay, so it's really kind of hard actually to explain this without showing you on the graphing calculator. And what I'd like you to do is see if you can get this value on the graphing calculator. We'll finish this particular example up in class, 87.89 feet. So what you do is you take your y1 and then you just plug in 1/2 of A. Okay, and you should get that. And I'm looking at this example in the book, so I don't have this rounded to the nearest 3 digits after the decimal. But anyway, that is your answer there for the part C. See if you can get that answer in your calculator. If you can't, we'll do this in class. We'll just kind of review this particular problem. Now, part D, determine the distance the ball had traveled. Now, the distance meaning the horizontal distance. It's not stated there, but that's what that means. Okay, since the ball was in the air for 4.688 seconds, to figure out the horizontal distance, you just have to figure out, well, what is x when the t value is 4.688. Okay, and you'll want to plug in the x into, let's say, your y2, and you should get about 608.92 feet. And like I said, we will cover this problem in class, and we'll review this just to make sure that you guys are all good with being able to plug this into your calculator. But I wanted to challenge you with one thing. I want you to bring one thing with you to class tomorrow or the next day, whenever you have it, and that is, I want you to make up your own. So let's do this. Your homework that you have to bring in is you have to make up your own scenario. Make up one scenario. Make up one scenario. Scenarios with SC, scenario. Just like a projectile motion kind of a problem. You need to have an initial velocity. You need to have an initial angle. And you need to have a story. So the first thing you're going to do is find an initial velocity. And I don't care what it is. You can say, little Johnny. Let's make a little story. So you could say, little Johnny kicked his soccer ball at an angle of 25 degrees, and he kicked it with an initial velocity of 50 feet per second. How far did the ball go? What was its max height? And how long was the ball in the air? And when was the ball at its max height? So things like that. Something like that. It could take you 1 minute to write this down. I want you to write it down neatly on a piece of paper, and you don't even have to solve it. I want you to just bring it to class. Okay, so that's your homework. If you don't have that, you're going to miss out on 2 points out of 5. Okay, and so make sure you do that. Okay, so I'll look for your notes, and I'll look for the little story with the initial velocity and the theta. So I'll see you in class.